Hey folks, this is Dr. Ayad here. I'm going to be going over some of the reaction stoichiometry homework that we have due this week. I think that these problems can be a real challenge for a lot of students, even if you feel like you understood the moles, if you understood the unit conversions, dimensional analysis, the balancing chemical equations. We are finally starting to bring all of that stuff together, and it's got a real world twist to it. We are now worried about exactly how much stuff we need to use, how much stuff can be produced, and so this starts to feel like it's very application-driven chemistry. I think that a lot of students start to struggle, but the good news is that if we just take it piece by piece, start by balancing the equations, start by setting up our dimensional analysis problems, I think that you'll find it's kind of the same stuff we have been doing up until now. So without further ado, let's get into this first problem. Okay. Consider the following reaction. Two sodiums, two hydrochloric acids are going to react to yield two sodium chlorides and one H2 molecule. You can assume that if you are given a equation that has these coefficients in front of the different compounds, that means that this has been balanced for you. I'm not going to try and trip you up by giving you something that has coefficients but isn't balanced, okay? So we don't need to worry about that for this first problem. It says how many moles of hydrogen gas can be produced if you begin with that many grams of HCl. I think that the can be is really important here because we're looking for the theoretical maximum yield. You're going to hear that phrase a lot, theoretical yield. What that really means is we're looking at the potential best case scenario. If we assume every single molecule reacts the way that it's supposed to, how much can you make? Now this is going to be different than what you do in your lab classes eventually, because in the real world, well, it's impossible to get every molecule, every atom to react. Stuff gets stuck to the glass. There are side reactions that might happen, and there is of course always going to be uncertainty in your measurements. So all of that stuff is going to contribute to decreased actual yields, but we're concerning ourselves with the theoretical yield for this first problem. I always think it's a good idea to just begin with what you know, and in this case, it's that many grams of HCl. It's going to be really important that we include both the unit, in this case grams, and the chemical identity, in this case HCl. The reason we want both those things is because we're going to be canceling both of them through the course of this first problem. Okay, I'm trying to figure out what? How many moles of H2. So I'm trying to find a link that's going to take me from grams to H2. Moles is kind of always going to be the central point. It's the goal that we're working to whenever we do these types of problems. If you are given something other than moles to start with, try and convert it to moles first, and then worry about converting that moles into whatever you want next. Okay, to get from grams of HCl to moles of HCl, I of course am going to need my periodic table. I'll take a look at the periodic table here. It shows us that we have 1.008 for the mass of hydrogen and 35.45 for my chlorine. I'm going to add those two values together, 1.008 plus 35.45, and that'll give me the molar mass for HCl. And we have 36.458. Technically speaking, you're not supposed to do any rounding until the very end of these problems. It could throw off the end result a little bit. You might find that I get lazy as I'm going through these because I know that there's like a 2% fudge factor built into all these problems. So I'm just going to stick with 4 sig figs for this first value. I'm trying to get rid of grams. And so that means that I want to stick the moles on top. 1 mole per 36.46 grams. I like to physically mark out my units every time I cancel them. By going through and slashing each one of those, it makes sure that I'm not forgetting to do any steps. It shows me what I have remaining. Right now, we're in terms of moles of HCl. You don't need to actually solve at this point. You don't need to do any math until you're at the very end of these problems. I like to set it all up first and then just knock it down on the calculator at the very end. Okay, from moles of HCl, I'm trying to convert into moles of hydrogen. We now need a conversion factor that'll take us from HCl to hydrogen. Now you might be thinking, well, how is it possible to memorize all of the different conversion factors for each compound or element into each other compound or element? Well, it's not possible, but it is possible to come up with a simple ratio based on our balanced chemical equations. That's why we worry about balancing these in the first place. We see that we have 2 HCl's up here on the reactant side of our equation, and 1 H2 over there on the product side. What this is telling me is that for every 2 HCl that react, we produce 1 H2. This sounds a lot like a conversion factor to me. So I want H2, which means I'm going to put the 1 H2 on top. On the bottom, I need to cancel something. I'm always thinking about what I can cancel, and HCl is a good candidate here. So I'll put the 2 HCl on the bottom, and now I can cancel the chemical identity out. And what do we have left? Well, we now have moles of H2. Those are the only descriptors remaining for our number here. And since we were looking for moles of H2 gas, I think it's time to calculate. I'll take my 5.47 times, divided by 36.46. You're always dividing if the value is on the bottom, and then divided again by 2. Now, in your calculator, it's very straightforward. You can enter those as just one continuous string, because when you're doing PEMDAS, the multiplication and division are technically the same priority. It doesn't matter which order you do them in. And I find that I have 0.07501 moles of H2. Now, the reason I included all of those values is because these first 2 zeros do not count as significant. They're just telling me the magnitude of the moles of H2. It's a very small amount, but I am still certain to 1, 2, 3, 4 significant figures, because that's how much I started with. You might be thinking, oh, well, isn't the 2 and the 1 from our balanced chemical equation going to tell us that we should only have 1 sig fig? I see what you're thinking with that, but this is an exact value. It's definitional. By definition, one of these equals 2 of those. And so you don't need to consider significant figures when you're using these as a conversion factor. And let's just check real quick to make sure I did that right. We should have 0.07501. Oh, you know what? It would help if I was on the correct problem. Phew. Okay. I was not going to be happy if I had to go back in and edit this to make me look right. Yeehaw. Okay, we did it. So these problems are definitely going to take some time to go through. I think I'm going to break this up into many small videos as opposed to one big one where I go through everything. So consider this the first part of many. Thanks for listening, and I hope to see you in the next one.